This video, we're going to prove the nth root test for series. If an is a series where eventually the terms are non-negative, that is, there exists a capital N so that whenever the subscripts of A are bigger than capital N, we no longer have any negative terms. And suppose that the limit of the nth root of a sub n is L. Then if L is if L is less than 1, this series converges. In case L is bigger than 1, this series will diverge. If L is 1, the test failed. It didn't give us any information about the convergence of a sub n. We say that the test is inconclusive. Now, when it comes to the proof, I need to prove each of those three cases. So, proof of A. Suppose the limit as n goes to infinity of the nth root of a sub n is equal to L, which is less than 1. So in terms of a number line, we have 1, we have L. Actually, let me move L over a little bit. We have L. Now, there's a number in between L and 1. There's many numbers between L and 1. 1 is L plus 1 all over 2. The middle of them. So there definitely does exist an R in between. Then there exists an R in the real numbers such that R is jammed between L and 1. Now, if we make the subscripts large enough, remember they're convergent on L, we make the subscripts large enough. So these here are the a sub n's. When n, little n, is large enough, they'll all be less than R. They'll all be less than R. If we let little n be fairly small, it is reasonable that some of the terms might equal R or be bigger than R, but not if the subscripts are large enough. Okay. Now remember, we're only talking about when the subscripts are bigger than capital N. Now, there exists an M bigger than N such that whenever N is bigger than M, we have that the nth root, I guess that should be the nth root, the nth root of a sub n is less than R. Okay, we have this property. But we also said that the terms are not negative. The reason I'm concerned about that is because I want to be able to say the following. Just want to sneak one little thing in there. The nth root of a sub n will be less than R, but they'll be non-negative. Now, if you have two terms, two values where two positive values, if you raise them to the same power, the inequality doesn't change. So I'm going to raise both of these to the nth power. So a sub n is less than r to the n. And this is for all n bigger than capital N. That is the summation of a sub n as n goes from bigger than n plus 1 to infinity. This is going to be less than the summation as n goes from n plus 1 to infinity of r sub n. Now, we know that r is less than 1. We have that right here. R is less than 1. But we have to be careful. This here is equal to the summation as n goes from 1 to infinity of r to the n minus the first n terms. N equals 1 to m of r sub n. Now, this converges. This here converges since r, which is positive, is less than 1. And this converges because it's a finite sum. It converges. So you subtract two convergent series, it converges. So this is less than a convergent series. Well, this is less than something that converges. So the summation as n goes from n plus 1 to infinity of a sub n converges. But we don't want that to converge. We want the whole sum to converge, not any terms missing. Now, the summation as n goes from 1 to infinity of a sub n, this is equal to the summation as n goes from 1 to m of a sub n, plus the summation as n goes from n plus 1 to infinity of a sub n. Well, we just shown that this converges, and the sum of m numbers converges, and when you add them, the result converges. That is, if L is less than 1, this converged. I know, we just shown it. Let us go on to part B. Suppose the limit as n goes to infinity of the nth root of a sub n is equal to L, which is bigger than 1. So basically we have 1, we have L, and I'm going to pick my R in between. Now there exists an R in the real numbers such that 1 is less than R, which is less than L. Now I want to pick the subscript a sub n large enough. So the nth root, the nth root of a sub n, if n is bigger than some special number, they're all less than R. Now, there exists a capital M, bigger than n. Why? Because this limit, these terms are getting closer and closer to L. there exists an m greater than n such that whenever the subscripts are bigger than m, the nth root, let's write that a little bit better, the nth root of a sub n's are bigger than r. They are bigger than r whenever n is bigger than m. Okay. Now for n bigger than m. So remember, r was bigger than 1, so it's bigger than 0. That is, both of these are positive. So I raise them both to the nth power. So the a sub n's are all bigger than r to the n. So the summation, let's write this first. For n bigger than m, the summation of a sub n as n goes from n plus 1 to infinity is greater than the summation as little n goes from n plus 1 to infinity of r to the n. But r is bigger than 1. This is going to diverge. And let us show that. Let me get a little bit more room going. Okay, now this is equal to the summation as n goes from 1 to infinity of r to n, which diverges. But it contains all of those terms that are being added up, but it has extra ones. It has the terms from n equals 1 to capital N. So let's take that away. N goes from n plus 1 to n goes from 1 to m of r to the n. Now this being a finite sum, it converges. But this diverges since r is bigger than 1. Remember, that was the whole premise here, that r was bigger than 1. Okay. So divergent sequence minus the converging one equals diverges. So we've shown that if the limit, you don't have to write this in the proof, we've shown that this limit diverges if L is bigger than 1. Okay, that was the whole part that we assumed, that L was bigger than 1. Now, let us do part C. Suppose the limit as n goes to infinity of the nth root of a sub n is 1. Now, if I can come up with two series where this limit is 1, and one of them converges and one of them diverges, then knowing that the limit is 1 didn't help at all. So we're going to consider these two series. Consider the summation of 1 over n, as n goes from 1 to infinity, and the summation from 1 to infinity of 1 over n squared. Now, the summation of the first one diverges, and the summation of the second one converges. That doesn't mean the test failed. I want to show that the nth root of this goes to 1, and the nth root of that also goes to 1. So that is what I'm going to show. The limit as n goes to infinity of 1 over n, the nth root. What does this equal? Well, we are going to write it slightly different. It's 1 over n. The nth root is 1 over n. We want to find out what this is. So how about we let y equal 1 over n raised to the 1 over n. And then we take the ln's of both sides. So ln of y is equal to, bring down the power, ln of 1 over n. So let's take the limit of both sides as n goes to infinity. The limit as n goes to infinity of ln of y is going to equal to the limit as n goes to infinity of, now I'm going to rewrite this where instead of multiplying by 1 over n, I divide by n. Now, what's in the brackets as n goes to infinity is going to 0. And ln of 0, or approaching 0, is negative infinity. And if n is going to infinity, well then n is going to infinity. So I'm going to use L'Hopital's rule. This is equal to the limit as n goes to infinity of, well, the derivative of ln of anything, you put the anything in the bottom and its derivative on top. And then that's the derivative of the numerator. And then the derivative of the denominator is 1. And my rule for dividing by 1 is don't bother. So let's clean up that fraction. This becomes negative 1 over n. What's in here is negative 1 over n. And basically, if we multiply top and bottom by 1 as n over n, this times this is 1. And like I said, don't bother dividing by 1. And this times this is negative 1 over n. Now this limit is 0. So what we have is the following. We have this is equal to 0. So the limit as n goes to infinity of ln of y equals 0. But I can I can put this and this as the power of e. This limit is equal to e to the 0, which is 1. So this here is the same as the limit. You know, I try to do it differently than I usually do. I hate what I'm doing. This means as n goes to infinity, ln of y approaches 0. But if ln of y is approaching 0, that means y is approaching 1. As n goes to infinity, y goes to 1. That is the limit as n goes to infinity of y is 1. But y was, right here, the nth root of 1 over n. So y was the nth root of 1 over n. So that limit is 1. So we can come back to the top and we could erase this question mark and say it's 1. Okay? When it comes to this one, the nth root of 1 over n is 1. Now I need to show that the nth root of that is also 1. So I want to show that the limit as n goes to infinity of the nth root of 1 over n squared, does it equal 1? So let's rewrite this a little bit differently. It's 1 over n squared to the 1 over n. And since you have n's in the power, that's not friendly. So we let y equals 1 over n squared to the 1 over n. We take ln of both sides, so we get 1 over n ln of 1 over n squared. And instead of multiplying by 1 over n, we can just divide by n. Now we take the limit of both sides as n goes to infinity. Ln of y is equal to the limit as n goes to infinity of ln of 1 over n squared over n. Now, what's in here, when n goes to infinity, goes to 0, and ln of 0 is negative infinity. When the argument approaches 0 from above, ln of it approaches negative infinity, and the bottom is also going to infinity. So we use L'Hopital's rule. Now, in anticipation of that, I'll write 1 over n squared as n to the negative 2 over n. So this is the limit as n goes to infinity. The derivative of ln of anything, you put the anything in the bottom and its derivative on top. That's the derivative of the numerator divided by the derivative of the denominator, which is 1. Don't bother dividing by 1. Let's clean up this argument. So we have the limit as n goes to infinity of negative 2 over n. What's in here is negative 2 over n. Just multiply top and bottom by n cubed. And this limit is 0. But like before, we now have the limit as n goes to infinity of ln of y equals 0. But what we just proved in the other page, that this is the same as the limit as n goes to infinity of y equaling 1. So you don't have to reinvent the wheel. We already established this in the last page. But what is y? That is the limit as n goes to infinity. Y was the nth root of 1 over n squared, which is 1. So, both of the nth roots of the two sequences that we started our part C with equaled 1. But one of those series diverges and the other one converges. Okay, so since since the limit as n goes to infinity of the nth root of a sub n equal 1 for both series, and the fact that one series converges while the other series diverges, we can conclude that the nth root test failed. Failed to give us any information. Yeah, I'll just say that. Why? Because if the limit is 1, the series could diverge, converge, or it could diverge. So the test was inconclusive. This finishes the proof for the nth root test. If you have any questions or concerns or comments or questions, leave a comment. Let me know how you like these videos. Show me a better way of doing these videos or some of these proofs. Show me where my mistakes are. Tell me how much you hate these videos. If you want me to prove a theorem, leave me a comment and I'll try to do that. But most of all, watch and learn.